Alright, in this example we're going to look at resistance proportional to velocity, and you guys can read through the derivation of this, but in essence the idea is that there are situations where the resistance that's encountered by an object is proportional to its velocity. As the object moves slower, it is less impeded by air resistance, and hence the resistance is proportional to the velocity of the object itself. You can read through the derivation, but it gets us down eventually to this formula, that velocity is equal to v sub 0 e to the negative k over mt, where v is velocity, v sub 0 is the initial velocity, k is a constant based on the particular object that's moving, and m is the mass. So let's go ahead and we'll look at example 2, which utilizes this formula. In example 2, we have a 10,000 kilogram truck that's coasting to a stop from a speed of 40 meters per second. The truck's motion obeys this equation, so it does have resistance proportional to its velocity, where k is equal to 200 kilograms per second. Alright, now our first question, about how long will it take the truck's speed to drop to 7 meters per second. So we're going to set up the model. We're looking for velocity here, and v sub 0 is 40 meters per second, and k is 200, and m, the mass of the truck, is 10,000. And so simplifying that, we get velocity is equal to 40 e to the, let's see, negative 200 over 10,000. Don't know why. Maybe because it's early in the morning as I'm recording this. My brain's not firing on all cylinders yet. Okay, it's negative 1/50th. Negative 1/50th t. Okay, and now we want to know how long it takes for the truck's speed to drop to 7 meters per second, so all we need to do is substitute 7 in for the velocity. And then we'll divide both sides by 40. And take the natural log of both sides. And then multiply both sides by negative 50. And so the time should be negative 50 times the natural log of 7 over 40. And then I'm going to go ahead and calculate that. And we've got negative 50 natural log of 7 over 40, and we get 87.148. And we're told here to round to the nearest tenth of a second, so we're going to say 87.1 seconds. That's how long it's going to take to slow down to that point. Alright, now part B of this example, we're trying to figure out how far the truck's going to coast before reaching a complete stop. So we have this velocity function, and what we're looking for now is we're looking for a distance traveled or a change in position. And what I'd like to do here is come up with a position function. So in order to come up with a position function from this, I'm going to integrate both sides. The integral with respect to t of velocity is going to be position, and the integral with respect to t on the left-hand side here, I'm going to utilize the substitution concept here. If I let u be negative 1/50th t, then d is going to be negative 1/50th t. And so when I integrate this, I'm going to have to multiply by negative 50. And so position is negative 2,000 e to the negative 1/50th t plus a constant. And now we look at the position at time 0 to figure out what our constant is. We let the position at time 0 be 0. And so that's negative 2,000 times e to the 0 plus c. So C ends up being 2,000. And so our position function ends up becoming position is equal to negative 2,000 e to the negative 1/50th t plus 2,000. And now in order to figure out how far it's going to coast before reaching a complete stop, I'm going to take the limit as t approaches infinity of this function, and that's going to tell me how far it travels before it stops. And so the limit as t approaches infinity of this whole thing, you think about what happens to the exponent as t grows infinitely large. It becomes an infinitely large negative value, and so this term approaches 0, and so we expect that this truck is going to coast 2,000 meters before it comes to a complete stop. Alright, that ends this video on resistance proportional to velocity. See you guys next time.